Now for our second example, we'll look at the decomposition of ozone. So here's the concentration data that's been collected over time. And we're going to do just what we did before. We'll look at the results using zero-order kinetics, first-order kinetics, and second-order kinetics, see what comes out of all that. So here's the equation for zero-order kinetics, and we'll plot the ozone concentration as a function of time. Does that appear to be a line to you? Well, let me get the best fit line and see. Now that's pretty obviously a curve. You go from left to right. The data starts above the line, goes below the line, then goes above the line. So I can fit a line to anything. It doesn't mean it's appropriate. So this was not appropriate. Therefore, it's not a zero-order reaction. So now we'll go to the next one, which is first order. And for first order kinetics, we need the natural log of the concentration. And there's the mathematical relationship for first order kinetics. And we'll plot the natural log of the concentration as a function of time and analyze the graph. Now I'll lay the best fit line on top of it, and that looks pretty darn good. Looks like it's a first order reaction. We're going to go ahead and look at second order kinetics just to check. So what do I need to do for second order? I need the reciprocal of the concentration. And then we're going to plot the reciprocal of those concentrations as a function of time. Now before even doing the graph, zero order, no. Looked like it was a first order. So if it really is a first order reaction, should the second order plot be linear? Well, if it really is a first order, this should not be linear. And it's not. It's pretty obviously a curve. So let's take a look at all three of the graphs briefly. 0, first, second. So with this method, one of them will best fit a straight line, and the others will not fit a straight line. And like I said in the first example, if none of these fit a line, then you have to go to more advanced techniques. You can keep jumping up the order. You can find using calculus equations that describe the higher orders. You can do fractional orders. But for us, it'll be zero or first or second order. Now, since the first order was the linear fit, we're going to use that line of best fit. Okay, now, let's see. Natural log of concentration versus time was a linear fit. That means it's first order. That means we know what the rate law is. It's first order with respect to ozone. And then, from the linear fit of y as a function of x, we can get the slope from the line. And for the slope units, notice it's 1 over seconds. And that's because when you use the natural log function, the units are factored out. So that natural log column doesn't have any units associated with it. And so that's why it's 1 over seconds. And then we did the slope because we want the rate constant. Well, the slope is minus the rate constant, or negative value of the rate constant. So we flip the sign, and there's our rate constant. So we have the rate law on top. We know the order because the natural log data best fit the straight line. Order is 1, and we have the rate constant.